Hi, in this video, I'm just going to tell you a little experience of myself that I had with MinHeap. So one of the earlier projects that I work on when I um, started in the industry was to optimize what's called an MP3 encoder. So an MP3 encoder is used to convert and compress digital music into the MP3 format. And this was very popular kind of maybe 2 decades ago. And it's still very popular today, although nowadays I think the AAC format is probably more popular. It does better compression and gives better quality than MP3 does. So now, just to roughly give you an idea what the MP3 encoder does, it's for those of you who know a little bit of digital signal processing from your electrical engineering class, and so you know that the sound waveforms they can be expressed in as signals in various frequency bands, right? This is kind of a an example of that. So in the horizontal axis, it's the frequency bands, and the frequency that human can hear is roughly from 20 hertz all the way to maybe 20,000 hertz. And the human speech is probably, if I remember correctly, probably around between the 1000 hertz to about 4000 hertz or so. And that's why we usually want the signal in this frequency band to be pretty high so that we can understand human speeches clearly. Now, so then one of the main goals of digital compression, what an MP3 encoder does, is to allocate given number of bits to maximize what's called a signal to noise ratio for each of the frequency bands. Number of bits really just kind of means, I mean, if you've seen these terminologies before, like, when you're encoding a piece of music, you have the choice of picking maybe 128 kilobits per second, or I don't know, 256 kilobits per second. So that just means for every second of sound, you have 256 kilobits to use for that one second to encode your music. Okay, so that's what that number means. And what the signal to noise ratio means is signal is the true data, right? That we want to keep. And then the noise, there are all sorts of sources of noise. And so we don't want to hear the noise, we want to hear the signals. So most of the time you want to maximize the signal to noise ratio. We just want to hear the signal. And that's kind of based on something called the psychoacoustic model. What the human hearing is sensitive to. So you have two kind of competing goal here, because the more bits you allocate to each frequency band, the higher the signal to noise ratio, but you only have so many bits. So you have to constantly figure out which band you can allocate your bits to. Okay, so in a very simplified view, to achieve the bit allocation process, we just do this, right? We just repeat these steps until we run out of bits. And these steps are: first, we find the frequency band with the lowest signal to noise ratio. Okay, so for that particular frequency band, we don't have enough signals, right? And once we find that band, we give that band some bits, and more bits helps to increase the signal to noise ratio. Okay, so you can imagine, once you give that band more bits, then maybe you didn't give enough, and that band will still have the lowest signal to noise ratio, or you increase the signal to noise ratio for that band enough such that another band would become the band with the lowest signal to noise ratio the next time you go through this loop. So, and that's kind of just the pseudocode, the high level view of what this process goes through. So the original implementation in the encoder store all the frequency band information in an array. So in order to find the band with the lowest signal to noise ratio, all I can do is do a linear search, right? And so we all know linear search is O of n, that is very slow. And when I did the profiling, this bit allocation process takes about one third of the entire encoding process, and it's the biggest one. One third is a lot of time. In this encoding process, it involves many other components as well, right? So 30% for one component is a whole lot. So I was trying to optimize how to make this faster, and then I happened to remember min heap that I learned when I was undergrad student. So that was in the data structure class, like the one you're taking right now. So I dug out my data structure textbook. I don't remember how to implement a min heap, but I dug out my textbook, and then just based on the code in the textbook, I implemented a min heap instead of an array to store the frequency band information. And then, so the min heap we just studied allows me to find the frequency band with the lowest signal to noise ratio in O of log of n. And I, at the time, I had to write my own implementation because, well, that was the entire encoder was done in C, and there wasn't any sort of standard library in C for min heap. I just want to mention here that I didn't mention earlier that Python actually has what's called a heap queue, and that implements a min heap for you. So if you ever need a min heap for Python, you can use the one we just wrote, or just use the one from the standard library. Okay. Now that's a digression. Anyway, so get back to the story. Once I implemented the min heap for the bit allocation, this essentially reduced the time that it takes to like almost nothing. So effectively, it reduced the overall encoding time by 30%. For a effort, I think it took me probably half a day back then to implement and debug it. So that's kind of a little story, a personal story that I remember very well because I actually put to good use something that I learned back in a class like this one. So the moral of the lesson is that you should study your data structure very well. So when you are presented with a particular task, you can know which is the right one that you can use.